Alright, this is chapter 7 homework for physics 201. This first one is just sort of a basic rotational motion problem. You have a propeller arm that is a length of 1.2 meters. That means that my radius of motion is 1.2 meters. It starts from rest, it's omega naught is equal to 0, and it begins to rotate counterclockwise with an angular acceleration of 2.7. Counterclockwise is positive 2.7. That's in radians per second squared. We'll assume this is radians per second as well. Part A, how long does it take for the propeller's angular speed to reach 5.7 radians per second? So our omega final now, or just omega, is going to be 5.7 radians per second. And we want to know what is t equal to. So in order to do that, we say omega equals omega naught plus alpha t, and then we solve this for t. See, that's 5.7 divided by alpha, which is 2.7. Check my units. That cancels. I'm left with the seconds in the numerator, which is what I want for time, and I get a time of 2.1 seconds. Alright, now part B, how many revolutions does it take for the propeller's angular speed to reach this 5.7 radians per second? So for part B, I'm looking for theta. It's equal to omega naught t. 1/2 alpha t squared. Omega naught is 0, so this whole term goes away. And I'm looking for theta. I have all this information. It's just 1/2 alpha, which is 2.7 radians per second squared, times t squared. Check out my units. They cancel, leave me with radians, and the answer is 6 radians. But I want to know this in revolutions. Specifically in revolutions, that's 6 over 2 pi, which is 0.95. Alright, what is the linear speed of the tip at 5.7 radians per second? You know, you have this thing that's going around in this direction, and we talk about the angular acceleration and the angular velocity. But this point is also traveling at a certain velocity, just a linear velocity, though albeit in a circular path. So we just want to know what is the linear speed. These are related. The linear quantities are related to the angular quantities by the radius, as we talked about in class. And the linear speed, v, is equal to omega times the radius. In general, you can get back to the linear quantity by multiplying the radial quantity by the radius. And you can look at the units. Omega is radians per second. Let's see, what is it? 5.7 radians per second times the radius, which was 1.2 meters, or the moment arm, if you will. And this will give me meters per second, because radians isn't really a real unit, and so we just get rid of the radians now, and we're just left with meters per second. All right, so part C, is 6.8 meters per second. That's the linear speed of the tip of this propeller. I also want to know what is the linear acceleration of the tip of the propeller. In a similar way, A is equal to alpha times r. Alpha is 2.7. Times r, which is 1.2. That gives me the acceleration, which is 3.2 meters per second squared. And then finally, what is the centripetal acceleration? Now this is the linear acceleration. I want to know what is the centripetal acceleration. That describes how the forces are changing the position or the direction of the velocity, the centripetal acceleration. And centripetal acceleration is equal to v squared over r. That's going to be 6.8 squared divided by 1.2, which is equal to 39 meters per second squared. All right, these are all pretty basic, just really basically using the equations and knowing how to use the equations. All right, a potter's wheel moves from rest to an angular speed of 0.2 revolutions per second in 30 seconds. Find its angular acceleration. I always just like to write down everything that I know. I know it starts out at rest. I know that the final angular speed is 0.2 revolutions per second. I'm going to go ahead and convert this into radians. In 1 revolution, there are 2 pi radians. So that gives me an omega of 1.3 radians per second. T is 30 seconds. And I'm looking for alpha. Right, all these numbers should be looking, all these variables should be looking familiar to you because they make up this expression or this equation, which we've used. And I solve for alpha. That gives me radians per second squared in units, and it's 0.043. Again, another basic rotational motion problem. These are very similar to ones that we've had in Chapter 2 and Chapter 3, just using these equations to figure out or to determine what is how to describe the motion of these particles, except they're now going in a circular path. All right, dentist drill starts from rest. After 3.2 seconds of constant angular acceleration, it turns at a rate of 2.51 times 10 to the 4th revolutions per minute. So after that amount of time, it's now traveling at this speed. I'm going to go and convert this into radians per second. I can see in particular I'm looking for the answer in radians, so I'm going to just express everything in radians per second, or radians or seconds. It's revolutions, 2 pi radians, 1 minute is what, 60 seconds? And that gives me my omega 2630. I want to know what is alpha. This is similar to what we had before. I say omega equals omega naught plus alpha t. See, omega naught was 0, so it's just 2630 over 3.2. And that gives me my alpha here. Just 822 radians per second squared. That's part A. Part B, determine the angle through which the drill rotates. For part B, I want to know what theta is. I know that theta is omega naught t plus 1/2 alpha t squared. So I can just plug this in. Omega naught is 0, so it's just 1/2 of 822. Times t squared, which is 3.2 seconds squared. That gives me radians, and I get 4210, 4,210 radians. That's part B. A certain light truck can go around a flat curve having a radius of 150 meters with a maximum speed of 32 meters per second. What maximum speed can it go around a curve having a radius of 75 meters? All right, the guiding principle here, let's say we have this curve, we have this truck going around this curve. This is an overhead view. This truck, as it comes around the curve, it wants to follow a straight path. So it has to have a force that's keeping it on the road, that's actually causing it to go into the circular path. As you know, we call that force the centripetal force, right? But this centripetal force has to be provided by something. Right? If you have a ball on a string, it's provided by the tension in the string. In this case, there's no string, but the centripetal force is provided by the static friction of the tires on the road. So this centripetal force is the static friction. The static friction provides the centripetal force, which causes your vehicle to go in a circular path. So my centripetal force is the static friction on the road, between the tire and the road. The reason it's static friction, by the way, this is an aside, but the reason it's static friction is this your tire. As it rolls along, this point, the point on the tire and the point on the road, are, with relation to one another, are not moving. Right? It's only if you skid that they start moving in relation to one another. Right? You always want static friction because that's the better friction. You don't want your tires to slide. Okay, we talked about that in class, but it's why we have static instead of kinetic friction. All right, so my centripetal force is the static frictional force. So I'm going to run with that. My centripetal force, I know, is mv squared over r. And my static frictional force is the normal force times this coefficient of static friction. However, because this truck is sitting on a flat curve, the weight is the same as the normal force because it's not banked. Okay, the weight is equal to the normal force. So I have mv squared over r equals the weight, which is m times g, times mu static friction. My masses cancel, which is a good thing because it don't have the mass. It's also a good thing because on curves on the road, they don't post masses for the different speed limits. You know, if it's icy and you're a certain mass and the speed limit is this and that, because it doesn't matter what your mass is. If you're heavy or light, it's going to still be the same maximum speed that you can travel. All right, so my masses cancel. I don't know the coefficient of static friction, all right? But I know the speed that I can travel with this. So I'm going to use that information to find the coefficient of static friction. So mu s is v squared over gr, and that's going to be 32 squared and r is 150 because I know what the maximum speed on the 150 meter curve is, and that gives me a coefficient of static friction of 0.70. All right, now I'm taking the same road but with a different curve, so the same material, so my surfaces aren't changing. The surface of the tire and the surface of the road aren't changing, so my coefficient of static friction is going to remain the same. But now I want to know what is the maximum speed with this new curve. So I take the same expression right here, but I'm going to solve it for v. That's going to be the square root of mu gr. It's the square root of 0.7 times 9.8 times r, which is 75. That's my new curve, and that gives me a maximum speed of 23 meters per second. All right. Notice that even though I've halved the width of the curve, or the radius of the curve, that I haven't halved the maximum speed that I can travel. Also notice that when I make a smaller radius curve, right, that's a sharper curve, the speed is decreased, as you would expect. All right, number 4. Drill bit rotating at 3,600 revolutions per minute rotates through 50 revolutions while coming to rest. Find its angular acceleration. Let's just write down what's given to us. Let's see, omega naught is 3,600 revolutions per minute. I'm going to go and convert that into radians per second. Times 2 pi divided by 60 gives me 380. Let me just write it out. 1 revolution, 2 pi radians, 1 minute, 60 seconds. And that gives me 380 radians per second. Alright, rotates through 50 revolutions, so that's theta. 50 revolutions. 50 times 2 pi, that's 300 radians, keeping proper sig figs. And now omega final, the final omega, which I'll just call omega, it's coming to rest. So this is a little bit different than other problems. It's actually coming to a rest, so it's slowing down. That means that when I actually get to my alpha, slowing down, it should be negative. My alpha should be negative. All right, so omega is 0. I think that's all that I know. I want to know what alpha is. All right, but in the course of this, I'm also I don't know what T or alpha is. Let's just write down my 2 equations. I know I have 2 unknowns, so I'm going to need 2 equations because I don't know what alpha or T. So I have theta is omega naught T plus 1/2 alpha T squared. I always find it useful too in these problems if you just have no idea what to do. Just write down the equations and start ticking off what you know and what you don't know. And then usually the solution will jump out at you. Omega equals omega naught plus alpha T. See, I don't know alpha here or here, and I don't know T here, here, or here. But I in particular want to know alpha. All right, so I need to create an expression that only has alpha in it. That means that I'm going to solve this for T. Omega minus omega naught over alpha. But since omega is 0, I'm just going to call this a minus omega naught over alpha. Now I'm going to take this, I'm going to plug it in here and here for T, and then I'll have an expression that only has alpha in it. That'll be the only unknown in that expression. All right, so theta equals omega naught minus omega naught over alpha. That's T plus 1/2 alpha minus omega naught over alpha squared. All right, so I'm trying to get to alpha. Pardon me, I had a mistake in my notes. So theta equals minus omega naught squared over alpha plus alpha omega naught squared over alpha squared over 2. Right? So the negative went away because it's squared. Now I can get rid of this alpha here and one of these. So notice that I have a common denominator. I'm just going to multiply both sides by alpha, by the angular acceleration. And then that gives me negative omega naught squared plus omega naught squared over 2. Right, because when I multiply through by alpha, that gets rid of this and this. Okay, so this, by the way, negative omega naught squared plus 1/2 omega naught squared is negative omega naught squared over 2. And I can now solve this for alpha. So alpha equals negative 2 theta. If I put in my numbers, the omega naught is 380, negative 380 squared over 2 times 300 radians. That gives me 240 radians per second squared. Oh, it has a negative on it. So that's my answer. You have to solve the system of equations. That's probably more like something that you might see on the test, where you have to solve a system of equations. So we're getting into some more difficult problems here, but these are more like you'll be tested on that you'll need to know how to do. Not exactly like this, of course, but something similar to this, where you have to solve the system of equations. All right, a boy swings a 15.7 kilogram stone in a horizontal circle with a radius of 0.98 meters. The string breaks under 370 newtons of tension. What is the maximum speed the stone can have? Well, the tension is the centripetal force. All right, so that centripetal force is 370 newtons. In fact, that's the maximum tension, or the maximum centripetal force, so that the string provides. So my tension, or my centripetal force, this is equal to 370. Centripetal force is mv squared over r. I want to know what is v. So let's see, that is it's my r 0.98 by m, it's 15.7. And that gives me my answer, which is 4.8 meters per second. A wheel has a constant angular acceleration of 3 radians per second squared. During a certain 2-second interval, it turns to an angle of 614 revolutions. Assuming that the wheel started from rest, how long has it been in motion at the start of this 2-second interval? This can be a little complicated. Let me just sketch out a little timeline. This is when the wheel started turning. It turns, and then you begin this 2-second interval. And during this 2-second interval, this time right here is 2 seconds. During this 2-second interval, it travels through 614 revolutions. All right, this was when it first started, so it had an omega equal to 0. All right, I want to know what is this time before this 2-second interval. How much time has passed? So, in order to find this, I want to find what is the time, what is this time at this point. All right. I also want to find out what is my omega naught at this point. And if I can find omega naught, that is omega naught at this particular point right here, at the beginning of that 2-second interval, then that will become my omega final for the previous interval. So let's first just consider the 2-second interval. All right, so I'm going to consider that 2-second interval on this left-hand side. And I don't know what omega naught is. I know that during that time, that t is equal to 2 seconds. And I also know that theta is equal to 614 revolutions. All right? So I know that theta equals omega naught t plus 1/2 alpha t squared. Now I also know what alpha is. It's 3 radians per second squared. All right, so I know everything here but omega naught. So I can solve this for omega naught. Omega naught equals theta minus 1/2 alpha t squared divided by t. That is 614. Let's see, I need to convert this. Theta is equal to 614 revolutions. That's equal to a theta of 3860 in radians. All right, so it's 3860 minus 1/2, 3 radians per second squared times 2 seconds squared divided by 2 seconds. And that gives me my omega naught to be 1927. It's going to be 1930 minus 3, which is 1927 radians per second. All right, so now this is a more basic problem. I'm going to consider this first interval of time. And for that interval, I don't know what the time is. All right, but I know that omega naught equals 0. I know that omega final, that is the omega at this point right here, is 1927. I just found that. And I know that alpha equals 3. So now this becomes a pretty simple problem. I just want to know time. Omega equals omega naught plus alpha t. So t is like this. So I get 1927 over 3. Excuse me, that should be radians per second, not radians per second squared, over 3. And that tells me the amount of time that has passed, 640 seconds. That's my answer. So during this time interval, 640 seconds passed. So again, we consider the 2-second interval. We find the initial velocity at that 2-second interval, and then that initial velocity becomes the final velocity for the first interval of time as it's speeding up to that speed. And then once we had that final velocity, we know its initial velocity is 0. That is at the very beginning of the spinning, and we can find the time. So it's in motion for a total of 642 seconds, including the 2-second interval. All right, a sample of blood is placed in a centrifuge of radius 15 centimeters. So the radius is 0.15 meters. The mass of a red blood cell is 3.0, 10 to the minus 16 kilograms. And the magnitude of the force acting on it as it settles out of the plasma is 4 times 10 to the minus 11. This is my centripetal force. It's the force that pulls those plasma cells out, those blood cells out of the plasma. So this is my centripetal force. Right, and I want to know how many revolutions per second should the centrifuge be operated. So I want to know what is omega, and I want to know particularly in revolutions per second. All right, so my centripetal force is mv squared over r. As we said, v is equal to omega r. So I can substitute that in, and I find an alternate expression for the centripetal force, m omega r squared over r, which is m omega squared r. So that's my new expression for the centripetal force, except now it's not dependent upon the velocity, it's dependent upon the angular velocity. It's just another way of expressing it. I can find that. My mass is given. It's 3 times 10 to the minus 16. Omega. Oh, I'm looking for omega. I'm sorry. Yeah, so let me erase this. Let's just solve this for omega. FC over MR. Oh, there should be 2 sig figs on these. I'm sorry. Sorry, I've been doing this for a while. It's getting a little old. That gives me 940 radians per second. I convert this into revolutions. In 1 revolution, there are 2 pi radians. That gives me the final answer, which is 150 revolutions per second. That's pretty fast. Every second it goes around 150 times.